Hello, we are Team 26074, and this is the Precision Automated Targeting System Project, PATS for short. Meet the team. My name is Jacqueline O'Neill. I am the team lead, and I'm majoring in aerospace engineering.
Francisco Calixto, procurement lead and optical engineer.
My name is Kaya Cheney. I'm the software lead, and I am a mechanical engineer.
Graham Gainey, projectile lead, aerospace and mechanical engineering.
My name's Hayden Mikuleski. I'm the integration lead, and I'm a mechanical engineer.
My name is Kyle Whitmore. I am the electrical lead, and I am the electrical and computer engineer.
While the project summary is here presented, I wanted to quickly include that the system includes a mobile target mounted on a controlled linear track and a high field of view camera capable of tracking motion across a 180-degree angular range. The goal of the project is to demonstrate a reliable moving target system capable of traveling 30 feet at speeds up to 15 miles per hour while remaining detectable and trackable by the targeting system.
Our software subsystem allows detection, autonomous tracking, as well as engaging the target using the Orbis launcher. The way we do this is that images captured by our Basler camera are pre-processed using OpenCV and then fed through an AI neural network called YOLO for object detection and tracking. One issue is that by default, these models run on the CPU of the computer instead of the GPU of the computer. And for AI inference networks or neural networks, GPU calculations are much faster than on the CPU, so we weren't getting the frame rate necessary. To fix this, we used TensorRT to essentially move the processing tasks from the CPU to the GPU, which allowed us to get vast improvement in the frame rate, moving from about 15 frames per second to about 30 frames per second. The target converts detections into angular offsets relative to the turret's core frame. From there, velocity as well as position can be estimated using the distance that the target is away, which is found by using the target's height. This allows us to predict where the target will be in the near future instead of where it is right now. On the control side, I experimented with PI loops as well as open loop control, but found that I had issues with latency mismatch as well as overshoot. The way to fix this was to add some feed-forward elements for the target so that we didn't lag behind it by using that velocity estimation from earlier. On the control side, I experimented with PID loops, PI loops, open loop control, closed loop control, and ultimately settled on combining a PI loop with a predictive element based off of a predicted velocity and position to move the set point forward so that we weren't lagging behind the target. One personal challenge for me is that I'm a mechanical engineer as the software lead. This means that I don't have all of the experience necessary to build out a whole UI system or create the targeting tracking on my own. So the way I got around this was through a lot of trial and error and talking to mentors and people around me to help get a better idea of how to structure the software and the control side of this project.
This is the final PATS mechanical system. It consists of two main parts. We have the lower and then the upper stanchion. These meet at a 6-inch diameter circle, and they meet at a servo horn for our 16.8 volt high torque servo. That allows the system to rotate. We have 3 columns on the inside with ball bearings that help support and stabilize some of our load. No pause in there. So the upper stanchion contains our tilt servo, and there's a couple components that help support that. There is a shaft as well as a ball bearing on the inside to minimize friction and keep it fairly rigid. We have a camera mounted on the top. We have a clamshell that goes over our blaster with grid plates so we could adjust our mounting location to better encapsulate the center of gravity. That's it. Overall, we had a successful mechanical system with the necessary rigidity and actuation being achieved. So to assemble the lower assembly, we weren't able to 3D print it all in one go, so we ended up plastic welding it. You can see those right here. For our lower assembly too, we had the support columns, and those actually snapped, all 3 of them. So we reinforced those with epoxy and metal rods on the inside. On the upper stanchion, we have a couple of angled cutouts here and a circle in the middle. That was for an external encoder we ended up not using. In addition to the pad system, we had to create our target system, which consists of an RC card with a target on it and our track to validate the pad's performance.
The optical system gives pads the sensing capability needed for autonomous detection and tracking. Our system uses a Bachelor H2 machine vision camera paired with a 6mm focal length and an f-number of 4. We selected the Bachelor camera for its strong image quality, reliable frame rates, USB 3 integration, and machine vision features such as global shutter, ROI, and pinging. Using the pipe-along interface, we were able to tune exposure, gain, frame rate for changing lighting conditions. The 6mm length was chosen through our optical calculations. The analysis showed about 87 pixels on target, providing enough detail and accurate detection and tracking. The f4 number aperture allowed sufficient light without excessive brightness or instability. A custom CAD mount was also designed to keep the camera aligned and secure during operation.
Our system is powered by a centralized high-voltage battery source which distributes energy safely and efficiently to all components. From the main bus, power is stepped down using DC to DC converters to meet the requirements of each subsystem. To ensure precise and reliable control, we use a teensy microcontroller to handle real-time tasks such as generating PWM signals for the servos, controlling LED indicators, and managing relay activation. The unique thing about our project is that we had to also build our own targeting system. So what we did is we retrofitted an RC car with an electronic speed controller, an RF relay module, and an Arduino microcontroller. Now what this does is it allows us to send up to 4 different signals using our remote for 4 different speed settings on the RC car. So we can have slow forward, fast forward, or fast reverse, and then we also have stop as well.
System performance was verified through incremental subsystem testing followed by full system integration testing. The system passed size and weight requirements with a final measured weight of 11.2 pounds, well below the 20-pound requirement. The system also presents a small stowed and deployed footprint, allowing for easy mobility. Stationary target testing confirmed detection capability between 10 and 35 feet, exceeding requirements. Moving target testing demonstrated successful engagement of targets traveling up to 13 miles per hour during outdoor conditions. Thermal testing confirmed stable operation for over 3 hours in outdoor temperatures near 90 degrees Fahrenheit. We additionally included an easy access emergency stop that was tested to produce immediate stoppage of power without damage to our system.
In summary, the Precision Autonomous Targeting System demonstrates successful integration between mechanical, electrical, optical, and software engineering into a working autonomous platform. Thank you so much for watching our video. Bear down.